Oh, geez. Hey, this is Coffee Compiler Club. We're here today to talk about compilers and language runtimes and garbage collections and typing systems and anything and everything to do with language implementations. And we have a guest speaker, Roberto Lozano, I should ask your pronunciation, who's here today to talk about his work on combining register allocation and instruction selection. And he is the guest speaker. So I'm going to lay out some ground rules and then I'll let him go. So we're being recorded live. Everyone said they're okay with that. It's fine. I ask you to mute your mic when you're not talking, so we don't have like barking dogs and stuff in the background. And I don't know, maybe that's it. So Roberto, why don't you take it away? And I'm going to hit the share screen button. And you should be able to share slides if you want. The slides are in the Discord chat. They're in the Zoom chat. Sorry, I'm not letting you go yet. Except that if people showed up late, I don't think it scrolls back. So I'm just going to cut and repaste the chat. All right, take it away, Roberto.
Hello, everyone. Can you see my slides?
Yes.
And you hear me well. Great. Thanks for having me. So yeah, it was nice to be in this audience, and I have a presentation which I prepared for an academic conference, and I have kind of reused it for this context. So if it gets a bit too academic or so, just let me know, and by all means interrupt me anytime. So I understand that this is more of this kind of a discussion, right, and an interactive thing, and not just me presenting and giving you facts and you listening, but so just interrupt me, criticize me anytime. Yeah, maybe I should talk a bit more about who I am. I am actually at this moment employed at Oracle as a hotspot compiler engineer. I'm actually maintaining this obscure just-in-time compiler called C2. Nobody's heard about. Before
so you're
this,
haunted by the ghost of Cliff Click daily.
Yes.
Before that, I spent a couple of years in Edinburgh researching, but before that, I did my PhD in Stockholm, Sweden. That's where I live, at the Royal Institute of Technology, and this is where I did the research that I want to present today. At that time, I was actually employed at a research institute. So I was doing the PhD at the university, but employed at the research institute. It was called SIX, now it's called RISE. And all this research was also carried in collaboration with Ericsson, the telecom company. We got lots of generous funding for this. And before that, I studied and was raised in Valencia, Spain. A beautiful city you might not have heard about, but take a chance to visit it if you're around anytime. It's a beautiful city, beautiful place. Right, back to the topic, constraint-based register allocation and instruction scheduling. This is work that I haven't just done myself, right? In the project, we had Mats Karlsson, Freide Hammar, another PhD student, Gabriel Hjort Åkerlund, and my PhD supervisor, Christian Schulte, who tragically passed away 3 years ago. Right, let's jump into it. So as I guess many or most of you in this context know about, this is how I think most compiler backends on Earth look like or are structured. You start with some intermediate code, an intermediate representation that it's independent of the processor you're generating code for. And then take it from there, you select the instructions for a certain processor. Then often you move into some kind of instruction scheduling or instruction ordering phase. And then you do register allocation, right? Where you assign registers to your program variables, a spill, and all that. Sometimes, depending on the processor you're generating code for, you might have a second phase of instruction scheduling to kind of reaccommodate all the new spilling instructions and register to register move copies that you have added and so on. And then finally, you generate assembly code. Right. So what we have here are three hard combinatorial problems, right? Hard in the complexity sense of view, like NP hard. Instruction selection is NP hard, scheduling NP hard, register allocation NP hard, and even worse, they are interdependent, right? So what you do in one of these stages will affect what happens in the next stage. Sometimes they are even conflicting. So the better job you do for scheduling, the worse it might get for register allocation, and the opposite. So there is no really optimal way in which you could order this to solve the interdependency problem. So what most conventional compilers do is to separate these three problems into stages, like you see in the pictures. First you do one, then you do another, and then you solve each of the problems with heuristics, some approximation. You almost never solve them optimally because they are NP hard. Now this has a number of problems. Obviously the code you generate is suboptimal, right? Because you are separating these interdependent problems and then you are solving them with heuristics. So you will never get the best possible code for them. And another problem, in my opinion, is that this approach is rather inflexible, in particular because of the use of heuristics. As you add new processors to your compiler backend, as you add new tricks, as you try to optimize and generate code for different objective functions, code size, energy, speed, or whatever, the compiler grows and grows ugly, and at some point, it becomes almost unmaintainable, the backend, right? I think we have all seen this. And this is just one anecdote. When I went into GCC to research a little bit more how register allocation was done there, I started reading in the GCC wiki. The first thing I saw was this sentence: Lord knows how GCC does register allocation right now. And this is not just a dunk on GCC. I think it's kind of a common trait, at least for the compilers that I have looked at, that there is someone very clever writing, for example, a new register allocator. It works fine, but then this person maybe moves away or whatever, and people add more tricks into it. And after like 20 years or something, or 25, it's almost to the point that you have to just throw it away and write a new register allocator by hand. I don't know whether this matches your experience, but at least that's what I have seen.
No, it's. I used to say that the typical lifetime of an optimizing compiler is what, 20 to 25 years. Then they got thrown away and rewritten, and C2's at that point.
And I think it's particularly bad for the backend part. That's my feeling. I don't know.
Yeah.
Right. So what did we try in this research? We tried to go the opposite approach. So we actually tried to integrate these problems, solve them together. And instead of solving them with heuristics, we try to solve them with combinatorial optimization to try to get the theoretical optimal best assembly code for a certain compilation unit. This is how the approach looks like. And actually, the research I did, it wasn't concerned with instruction selection. So we did instruction selection with heuristics, just like before. And then rather than going right away to scheduling or register allocation and trying to solve them with heuristics, what we do is that we generate combinatorial models of the problem. A model that describes how the problem looks like, what are the semantics of the program, what are the constraints of the processor architecture, and so on. Then we take a model for register allocation and a model for scheduling and combine them into a single model. And that's a pretty cool thing of this combinatorial modeling approach, is that you can actually combine problems. It's very composable as opposed to heuristics. Then we take this giant problem that describes the entire register allocation and instruction scheduling space of choices that you might take there, and we give it to a constraint solver, and we tell the solver, optimize for this or for that.
Okay, so how fast is that?
Yeah, how fast is that? Well, yeah, it takes some time, obviously. Yeah, that's undeniable.
What kind of constraint solver do you use?
So here we use constraint programming. There are other techniques like SAT solving and integer programming. SNT, right? The kind of solvers we use resemble most, SNT solvers, I would say, but a little bit more tailored towards optimization.
Okay.
Right. Yes, and if you're patient enough, you get your optimal assembly code. Right. So the advantages of this are quite obvious. It is optimal, but then we should really review a little bit what do I mean by optimal, right? It is optimal according to a cost model. a static cost model, right, of the processor, latencies, delays, and things like that. So the approach is only as good as your cost model, right? And it is flexible. I think that's perhaps the key advantage of this. It is quite simple to retarget this to a different processor, to actually switch objective function and optimize for something totally different without having to rewrite all your heuristics and so on. Yeah. Okay, so here by
I
contributions,
assume
I mean,
that's pluggable, so you could do weights. I care this much about how big my binary is and this much about how fast it is.
right, yeah, that's a part that we didn't research too much, the multi-objective thing, but that will be something fascinating, I think, to look at. I
The
mean,
main objective is
I feel like
optimal
balancing that
code, I
objective
presume.
function would be non-trivial.
yeah, it would be non-trivial. I mean, there are approaches to solve multiple objective optimization functions problems, but this is really like state-of-the-art research in combinatorial optimization. It's
But
definitely
for now, the
non-trivial.
main objective is optimal code execution.
Speed, execution speed.
Optimal execution.
We tried a couple of them just to illustrate this idea that we can switch among. So we just tried speed and code size, you know, the obvious kind of choices that you can compare against conventional compilers.
Seems like a good two goals.
Yeah. Yeah, so this is more contributions in the academic sense. I don't know whether that's too interesting here. This comes from an academic conference paper, right? So you always need to state what are my academic contributions, what is the novelty here, and so on. All right, so combinatorial approach, and I claim that this is the first combinatorial approach that is practical. And remember, practical compared to other combinatorial approaches. Okay,
Okay, fine. If I'm in a JIT and it takes 5 hours for the SMT solver to return, I don't know.
right, exactly. This is and what do I mean by practical? To be a little bit more specific, it is the first time that we actually model register allocation and instruction scheduling in its entirety. So all, as many of you know here, register allocation in the academic literature sometimes is reduced to, like, you know, graph coloring and then perhaps spilling or something, but there are many more sub-problems that are typically solved with register allocation, like coalescing, life range splitting, rematerialization, and all that. And we try to incorporate all these problems so that we could actually compete against a conventional compiler that does all of this. And the previous approaches, academic approaches, didn't do that. Then I would say it's fairly scalable for the amount of stuff that is in the model, right? And again, fairly scalable in comparison to previous related approaches, not fairly scalable in comparison to C2, right? And last but not least, it generates executable code. It might sound obvious, but this wasn't the case either for previous approaches. So the previous approaches in the literature were very academic, so to say, right? So here we try to do something more practical and effective, of course. So we could show that we can generate better code than conventional backends, and I will come back to that, how much better and so on. And the key to all of this is, I would say, the use of constraint programming. Like we have mentioned, there are many combinatorial optimization techniques, but we found that constraint programming in particular has a number of properties that make it more suitable for solving this problem. Okay?
Yeah.
But what is constraint programming? So in constraint programming, like in other combinatorial optimizations, we have kind of two phases. First, we model our problem, and then we give this model to a solver that does the job for us, right? A model of the problem consists of a number of variables, and the variables capture the kind of choices that you want to express. In our context, for example, a choice might be, do I spill this or do I spill that? Do I schedule this instruction here or there? And so on. Then we have constraints, which are just relations among these variables. Something like, if I assign this temporary to this register, then I must assign this temporary to some other register because they interfere, or something like that. So relations among variables. And finally, modeling consists often of an objective function that tells you how good a set of choices is according to some cost function. This is a very simple example of what a combinatorial model might look like. You maximize some variable, that is the objective function, subject to a number of relations among different variables. Okay. Then we give this model to a constraint solver, and a constraint solver in particular has two solving techniques. And I guess many of you have solved a Sudoku before in your life. And if you have, then you must have probably a good intuition of what the constraint solver does. Because it's kind of the same procedure in a more general and systematic way. So what the solver does, first of all, is propagation. That is, it looks at the choices that you have taken so far as a subset of all possible choices, and then it tries to determine what choices that remain are valid according to the constraints, and tries to discard choices which are no longer possible. This is, in the Sudoku world, would be the same as looking at a certain cell, looking at the values that remain that are possible for that cell, and then looking at all the rows and columns around it, and then discarding values for that cell that appear in the row or the column, right? But this only doesn't give you the optimal solution, right? Because we are dealing with NP-hard problems here. So at some point, we need to resort to search. Basically, you take a guess, right? You take a guess, and then you go on propagating. Take a guess, go propagating. At some point, you might hit a failure or a contradiction, then you need to backtrack and then try something else. Just like in the very hard Sudokus, where you have to take your pencil and then draw a very thin number and a very thin 5 there, and then go on. And then at some point, you might run out of values and you need to remove the 5 and then try something else. That's kind of the search here, right? And you repeat these two steps, propagation and search, and there are other tricks that the solvers do, but this is the main idea. And finally, you get your solution. The problem is that the first model that you write tends to be quite bad in terms of performance. So sometimes, or very often, you need to come back to the model and start doing reformulations and things that help the solver reason further. So this is a whole black art about reformulations and remodeling, right? So in theory, sometimes when people sell combinatorial optimization, they sell it as, write this very simple model and then you let the solver do the work. But in practice, you need to do a little bit more work to let the solver do a good job. For
a fast job, because it would return the same optimal answer every time, I assume.
Exactly. But very often the first model you write maybe gives you, the optimal solution for up to instances of whatever, say 10 size. And then your job is to reformulate the model, try to push this boundary. And of course, you're dealing with NP-hard problems, so you always hit the wall, right, at some point.
Yeah, but when you say size 10, let's assume that you're counting, say, instructions. That's a very small function. Is this growing with the size? Like, here's 1,000 instructions in a compilation unit. Here's 100,000. I
have a picture that shows you more or less scalability. Should I jump right to it, or do you want me to hold on a little bit and tell you more
if
background?
It's coming up, just roll through. You can probably go a little faster, or at least for me, you can. I don't know where everyone else thinks you're at the right speed or not. Roll on.
Faster, okay. So a key feature that help the solver make a faster job is the use of what we call global constraints in constraint programming. And global constraints are relations that among many variables that capture kind of common substructures in problems. So for example, here you see that you have variables x, y, z. They must be pairwise different. Then we have a global constraint that is called all different that captures this. And global constraints are good for conciseness of the model, which is good, fewer constraints and so on. But more importantly, they let the solver do better propagation, so stronger reasoning, basically, and thus less search. So it can exponentially improve the performance of the solver if you can express relations. So it's often, when you do constraint programming, you're really looking for these global constraints.
My question is, doesn't it accumulating that much global constraints doesn't slow the problem more and more, because you have to consult always, you are consistent with the global constraints?
So yeah, the propagation phase will be slower for sure, but then every time you reduce search, you really win, right? Because you're removing exponentially propagation steps, right? So you are increasing the propagation, the cost of propagation by some factor. Typically, propagation is fast even for these global constraints, but yeah, maybe you're increasing it linearly or even quadratically, but then you are removing exponentially many propagation steps, right? So it's almost always a win to do global constraints.
Okay.
Right. So how does the model look like for register allocation and instruction scheduling? The model we proposed. Let's go step by step here. Okay, register assignment. Maybe let me know if this is too basic, and then I can just speed run to it. I mean, maybe you don't want to know what register assignment is.
Well, I want to see how you do the mapping of the model, but I'm comfortable with register allocators. So.
Yeah. Okay, so I will go very quickly. This is just an example of possible register. I call virtual variables temporaries for some reason. So just if you don't get confused by that, right? So when I say temporaries, think virtual variables or program variables or whatever. So this will be a naive register allocation, right? Because we could just in theory assign one different register to each temporary, but of course we have the problem that we have a limited number of registers in our processor. So we want to reduce as much as possible. For example, like this, we assign the same register 1 to temporaries 1, 3, and 4. Fine. The question is, when can two temporaries reuse a register? For that, we need to go to the notion of liveness. What is the life range of a temporary? Basically, informally, when the temporary might be needed. Right? Those are the program points that form the life range. And in this context, it's really between the definition and the last use of a temporary. I'm using SSA as a starting point, right? So in this trivial example, T2 starts being live when it's defined by MAL and then dies when it's last used by ADD. So with this notion now, we can answer when can two temporaries reuse a register if the life ranges do not interfere, right? If they do not overlap in time. So in this example here, for example, T3 and T4, they can use the same register. The life ranges do not interfere, while T2 and T3 cannot use the same register because they interfere, right?
And T1 and T3 can though, right?
Right, exactly. T1 and T3 do not interfere, so they could also.
So this is a two coloring.
Yeah. Okay. So in our model, what we do is that we define a variable for each temporary telling us to which register it is assigned, right? And then we formulate the register assignment as a rectangle packing problem. So for each temporary life range that we have in the register assignment domain, we form a rectangle in the rectangle packing domain. And then the fact or the constraint that interfering temporaries cannot share registers in this rectangle packing domain becomes nothing other than the rectangles cannot overlap in a two-dimensional space. Right? Why do we do this transformation? Is because we have a global constraint that is called no overlap that takes a bunch of rectangles and makes sure that they do not overlap. Right?
So the red rectangles have length, but they're sort of infinitely thin. Is that how we to think about it? It's not a 2D problem.
In the basic version, you're right. So okay, just to show an example to clarify this. Here the life ranges, and then they become rectangles, right? You pack them in this two-dimensional space. Yeah. Right. Horizontally, you have registers. Vertically, you have time or program points if you want. Yeah. And yes, in the basic model, each rectangle will have the same width. However, if we want to model register aliasing, this becomes interesting, right? Because all of a sudden you will have temporaries of width 2 corresponding to say 64 bits. Temporaries and then temporaries of width 1 corresponding to 32 and so on.
I get another related question. What does this look like with the control flow graph? You're showing a single basic block, but if you have complex branching control flow,
I'll come back to that in quite soon, right? Just a couple of slides, I think, ahead.
Go on, yeah.
Yeah. So I try to show the model how it's built incrementally, right? So yeah, this is for a single basic block as of now. And yeah. And this is not something that we came up with. There was a paper in PLDI 2008 about this. What we did is to take that paradigm and to plug it into the constraint programming framework, right? Because in constraint programming, we happen to already have specialized reasoning for this kind of rectangle packing problems that we can benefit from. Right, this no overlap constraint is something that most constraint programming solvers will actually implement. Right, and like I mentioned before, there are many other register allocation subproblems, and we try to model all of them. If you're interested later on, I can tell you more about the modeling of all these other problems, but now in interest of time, I just list them. But we model spilling, life range splitting, coalescing. Register packing is what I mean when you handle register aliasing, right? Basically temporaries of different widths, registers of different widths, and then you try to, in some processors, you can pack like one temporary in the high part of a register and another one in the low part and things like that. And we can do that easily through this rectangle packing paradigm. Load store optimization, this is basically when you have to spill, you have a choice whether to spill everywhere, and then basically you do the store, and then you do a load for every use of the value that you have spilled. Or you might be sometimes a little bit more clever and realize that I can store here, but then I can reload here, and then I can use the reloaded value. I don't want to reload again later on because the register pressure is not as high or something. The model captures that. Rematerialization in its most basic form, that is just constant rematerialization, basically. But I think that's more or less the common thing in most conventional compilers I know. And then multi-allocation, this is a term that I made up, so I don't know how to express otherwise the fact that we can spill a value and then have it live in memory, but also keep it live in some register for a number of cycles. This is beneficial in some contexts, and some models before didn't allow it, and we tried to capture this, and we saw that there were some benefits.
Yeah, it happens in C2 as well.
Right.
But if it changes, you need to spill it again. You need to rewrite it out.
It's a different value if it changes.
Right.
Yeah, that's fair.
Yeah, exactly. Oh yeah, global scope will come in a minute, how we deal with control flow. But before that, the instruction scheduling part. What is instruction scheduling in our view is just a mapping from instructions to time points, issue cycles in this case. And here we're lucky too, because scheduling with resources is kind of the bread and butter of constraint programming solvers. So there's lots of specialized reasoning for that too. Basically, what you do here is that you define a variable for each instruction that tells you the cycle in which the instruction is scheduled. And then you add some constraints constrain basically whenever you have a data precedence, this constrains the schedule, the relative schedule of the definer and user. And then we have resource constraints, modeling things like functional units. And if you are doing scheduling for very long instruction word processors, like we did, then the width of the bundle and things like that. And yeah, like I said, most solvers have specialized reasoning for this too. So we got this for free, so to say. In particular, there is this global constraint that is called cumulative for dealing with resources and use of resources over time. And we use that. Now you might wonder, how does this connect to the register allocation problem? So the connection, if you think about it, or at least in our model, is to the life ranges, right? Basically, what we do here is that we make the top and the bottom of each rectangle that corresponds to a life range variable, where the top depends on the cycle in which the definer is issued, and then the bottom depends on the cycle in which the last user is issued. Right, and then as you are doing scheduling, you are basically affecting the length and placement of these rectangles, right? And this is where the connection happens between register allocation and local instruction scheduling, right? I must mention we do local instruction scheduling, not global. That will be future work. Any question about that? You are mute.
Sorry. So you don't, if you know you have a streaming load through an array, for instance, you know it has long latency to load. It's always cache missing to load. You're not going to haul it above some basic block boundary. Like somebody picked a basic block in the first place. How did they pick it in the first place?
Oh, actually, this part of global scheduling we do, like long latencies across basic blocks.
Okay.
With that part we take into account. but we cannot like basically we don't do global code motion, right?
Okay.
So we couldn't move the instruction all together to the. But we take into account the long latencies across basic block boundaries that we do. Yeah, we found that essential for some type loops and so. Yeah. Global scope. So our aim here is to extend the rectangle packing model to whole functions with arbitrary contour flow rather than just basic blocks. So what do we do with temporaries that are live in multiple basic blocks? Like in this example, you have a diamond and then you have T1 defined on top and then used later on. So it's live through these 4 basic blocks. So what we do basically is we decompose this temporary into 4 local temporaries. So we apply this program transformation before we formulate the constraint model. We define this refinement of SSA, if you want, which we call linear SSA, because the life range is turned to be linear. So that basically the idea here is that we define T1 for the first block, and then T2, T3, and T4. So there are 4 different temporaries now, 1 for each block, and then we have a little nice rectangle for each block. And then, of course, we keep track of which temporaries correspond originally to the same virtual register or to the same temporary, right? So we define this congruence, saying that, for example, T1 and T2, they're congruent because they represent the life range of the same original temporary. Right, and then we have the constraint that congruent temporaries get the same register across basic block boundaries, right? So that they kind of glue together nicely across boundaries. So this will be the contour flow graph and the register assignment for factorial, little factorial function, right? And we see, for example, that, can you see my mouse pointer? I guess not.
I can see it.
We can.
You can? So for example, we have T2 in this initial basic block, it's assigned to register 2 here. Then we have a constraint that says that T4, because T4 is congruent to T2, then T4 needs to be assigned to the same register basically here. So when you jump from this block to this block, you find the temporary in the same register. Right?
Yeah.
So yeah, we get lots of temporaries by doing this decomposition. Right, so the number of names in our intermediate representation explodes, but this is the list of our problems when it comes to scalability, right? Yeah, and how we put all of this together? This is what the model looks like in all its glory, and it's actually pretty compact for the amount of subproblems that are captured here, but I'm not going to go through it in detail. I just want to highlight a few features of this model. First of all, note that we have a generic objective function. This is an objective function that we can instantiate to optimize for speed, size. It's basically just a weighted function of the cost of each basic block. And the way you define the cost of the basic blocks and the weight of the basic block gives you what you optimize for. So if you want to optimize for speed, for example, the weight of a basic block will be the estimated execution frequency of the block. And then the cost of a basic block will be the make span, right? Or the number of cycles that it takes to execute the block. Then you have the speed optimization. If you want to optimize for code size, then the weight of a basic block becomes just 1. All basic blocks are equally important. They contribute the same to the total size of the function. And then the cost becomes just the sum of the size of each instruction in the block, right? So this is a totally generic objective function, and it's the only thing that you need to change to let the solver know, and then the solver will take different choices, and will generate code quite differently, actually, depending on what you tell it to do. Another feature that's interesting to remark is that the model is compact, in the sense that the number of variables and constraints defined in the model are independent of the number of registers and also the number of cycles in it. So if you think about this 2-dimensional space for register assignment, doesn't matter how wide this rectangle is or how tall it is, basically, for the compactness of the model. The model will be as large, or
this is the model definition is large as opposed to the model This blow up of internal states when you're solving.
Oh, yeah, perhaps. I mean, of course, there are techniques to try to contain it. Yeah, the search space is larger for sure. But then in practice, it matters typically a lot whether you combinatorial, I mean, the number of variables and constraints in your combinatorial model, because the solver will just generate more data structures and things for each variable and for each constraint. So we tried some model reformulations that added constraints that in the number of registers, for example, available, or in the length of a basic block, and we found that this really killed scalability, or the little scalability that we get was totally killed by that, right? So yeah. And the key for getting this is really that we use these global constraints I mentioned before. If you try to model this, for example, with SAT solving, in many parts of the model, you will have to define constraints for each pair of temporaries, for example, like quadratic number of constraints, or for each register and for each blah blah blah, you will have to generate a little constraint, and that will probably explode, right? So we have global constraints for rectangle packing and for scheduling. So that's really what gives it the advantage.
We appreciate the non-Greek symbols, though.
Thanks. The first version had Greek symbols, and my supervisor told me to write it better in English, and I think that was wise.
That was excellent decision.
Yeah, the model is explained in a more, how to say, in a easier, simpler way in the paper. So you can look at all the papers. Cliff added the link to the project page, I think.
Yeah, I pushed it around. Yeah.
And you only need to read the paper published in TOPLAS, Transactions of Programming Languages and Systems. I think this captures pretty much everything.
Is that linked into the Unison code GitHub?
Yes.
Yes. Okay.
Okay, let's move on to the results.
Yeah.
So we wanted to find out how practical is the approach really, and for that we looked at the scalability, and then how effective. So we evaluated the code quality for speed and for size. We weren't in a position because of the scalability of compiling whole benchmarks, right? Like lots of functions. So what we did here is we sampled functions out of benchmark suites like media events for embedded and signal processing kind of applications, and spec CPU for the usual thing that compiler researchers do. And we sampled functions of what we call medium size, that is up to 1,000 instructions. Beyond 1,000 instructions, that's already pushing it.
Okay. Yeah, I would have said, okay, fine. Yeah, there's some tail curve on the size of compilation units, but 1,000 seems small to me.
Yeah. So we actually measure the distribution and of all the functions that appear in these benchmarks with normal inlining policies.
By C2?
No. So we use LLVM as a baseline. Sorry,
Right,
that comes later.
Yeah. Well, I'm curious because I C2's allocator, I worked hard to make it robust for over inlining and over spilling effects. And so I then pumped up the inlining a lot. So I have much bigger compilation units typically, I think. And of course, whatever happened after I left for 20 years. So I'm curious to see what the distribution is on C2 compiled methods, which is unrelated to your problem. So you should carry on and I'll shut up.
I don't know, but when we look at it for Clang and LLVM, we found that more than, what was it, more 95% or something of the functions were smaller than 1,000 instructions. So not too bad. But of course, there will always be functions which are totally out of scope for this technique. That's for sure.
It's the profile directed inlining that C2 does. The hot code always inlines the bejeebers out of things.
Right. Clang probably needs to be more conservative.
Probably doesn't have profile data, so he's more conservative.
Right.
Yeah.
It would be interesting to repeat the experiment with profile guided optimizations. And
curious to know that one too. All right, fine. Yeah.
So like I said, this research was done some years ago. So we use a baseline which is a little bit aged right now, LLVM 3.08. That's what we have. And we use this baseline for two aims really. One of them, the obvious one, is for comparison to see how good code quality we were emitting in relation to LLVM. But we also use it in a different way, use it as a quality lower bound. So basically we run LLVM, get the solution, compute the cost according to Unison's cost model, and then actually give it the solver a constraint, an actual constraint saying, you must generate code that is better than this, right, in a constraint. And this is interesting because it actually helps the solver a lot. Sometimes you will give this constraint to the solver will come back to you directly and say like, sorry, there isn't such a solution. Then you know that the LVM's code was actually optimal. This happened now and then. And now I must repeat, of course, optimal according to our model.
You get issues where because your model was incorrect or suboptimal, that LLVM would beat you and you'd have to go back and adjust your model.
We had to do that. Yes, that's how we figured out that, you know, we had to have a very complete model, right? So the first iterations, for example, we didn't have rematerialization. And then for some functions, we found that our optimal solution was worse than that of LLVM, right? Because that's why I insist it's important to have a complete combinatorial model, right? And then we went back and then added rematerialization to the model and so on. In the last version, I don't remember seeing this anymore, right? So
it sounds like it convinced you that LLVM was actually doing a fairly good job already.
Yeah, we'll see more specific results, but yeah, wasn't too bad. What processors did we look at? So yeah, remember this was set as a collaboration with Ericsson, right? And in this collaboration, basically we were looking at how to generate good code for Ericsson's custom hardware for base station signal processing and things like that, right? So this is the angle that we have here, generating code mostly for embedded systems and things like that. So we picked for evaluation processors in that space, and one of them is Hexagon. Maybe not very well known, I don't know, but it's a digital signal processor in a Snapdragon system on chip, so it's actually quite widely deployed, even if it's not very maybe well known. And it's a very long instruction word processor, which makes it very interesting for studying this combination of register allocation and instruction scheduling. Are you familiar with very long instruction word architectures?
Only Intel's Titanium.
Sorry, Aaron, say again.
Intel's Titanium is the only very long instruction word I know of.
I had to port
not looked at
hotspot
anything.
to Titanium. Oh, geez, what a nightmare. Fine, but yes, I'm comfortable with the LAWs. Fine.
Yeah. So yeah, it's the same idea as Titanium, just typically wider maybe and so on. And then small versions of ARM and the MIPS 32 for reference, basically. And notice that all of these processors are in order, right? They're not out of order. Modeling out of order is really future work if you want, right? We actually did an experiment where we modeled x86 as if it was an in-order processor. And the cost model was so off that whatever the solver told you about the quality of the code didn't really apply in practice, right? So there's more research to be done there. And we gave the solver 15 minutes per function as a time limit. But as you will see soon, often it will finish before that. Right, so finally, scalability. This is the plot that I mentioned before, Cliff. And here I show all the functions as dots in a second. And then on one scale, we have, on one axis, we have the number of instructions of the function, and the other one, the number of seconds it took to find the optimal solution, right? So this is how it looks like for MIPS. You see that we solve maybe, so the smallest functions get solved in around like 1 second. These are tiny functions. And then, yeah, solving time grows and grows to optimal up to hundreds of seconds and so on for functions of, you know, more than 100 instructions. That is for MIPS. This is for ARM, a little bit more scalable for some reason, which we honestly don't fully understand. So understanding why a solver is doing well or not doing well is also kind of an art. It's not as bad as in machine learning, as explaining things in machine learning, but it's also not trivial to figure out why a solver is performing well or not, right? So and why it is doing better for ARM than MIPS, we have some hypotheses, but we don't know for sure. And then interestingly, for Hexagon, we got the best scalability, which was surprising to us because for very long instruction board processor, the solution space is bigger, right? You need to decide which instructions are running in parallel with which as your schedule. So in principle, it should be harder for the solver, not easier, but actually the solver had a better time generating code for hexagon. Here we generate optimal code for functions of 946 instructions in a few minutes, right? And yeah, in the time scale of combinatorial approaches, this is a success. Right, so I claim it scales to medium-sized functions, where medium size is smaller than 1,000. Other people might have other definitions of medium-sized. But of course, it's very clear that the scalability depends a lot on the processor, and yeah, we don't know exactly why.
So if you were going to put this in a JIT, you would very much reserve it for only the very hottest stuff.
Oh, you'd have to be doing something for a while before you would stop and wander off for 10 minutes to go compute, generate a new method.
If you have a tiered compilation scheme, then this will be tier 10.
Yeah,
you know,
exactly. Yeah.
Where only a very, very carefully selected number of methods are compiled. Yeah.
You could draw the median curve on that. It's a log scale. Yeah, you draw a median line for each of your 3 chips. You want to make it more clear how they scale the differences.
Yeah, should do that. Yes. Yeah, but that is kind of the use case. I mean, we don't advocate necessarily using this in a JIT compilation setup. But if you wanted to use this in practice, this is what we advocate, is actually selecting the functions that matter most and only compiling them with this approach, right? Not the entire code base. That wouldn't really work. But if you find, 5 or 10 functions which take out most of the runtime, which is maybe not as uncommon, then maybe you can afford
compilation for embedded systems.
Right, exactly. In embedded systems, people is willing often to spend more time compiling.
Or imagine big tile video games that ship to millions of people. What is a few hours of compilation time in that case?
Maybe you.
I was thinking like the YouTube transcoding library. It does a lot of turning things.
That one I would buy, but the game issue is that you're typically churning development cycles endlessly, and this is too slow for your dev cycle. So if you want to go push a version out and you change on to your compiler flags to try some different compilation, it's untested by anything you've done in the past years of development. This is a big thing that was going around when I was doing compilers in all kinds of public forums, and the answer was no one ever shipped anything in product that they didn't test aggressively, vigorously on everyone's desktop all the time. So many people shipped -debug binaries because those are the binaries they could trust. I'm serious. There were a few folks that went to -02, and no one in the right mind did profile directed feedback on a production server. They only did it for benchmarks. So when Java came along and did, all the time continuous profile directed feedback, that was like scary, wow, cool, but like we can't do that. Well, other people can't, because that's the only way Hotspot runs. All the bugs got knocked out of it. But if you're doing profile directed feedback on Clang and it's not the thing that shipped on 1 million people's desks every day, you only take a few such compiler bugs and your reputation's shot.
Yeah, that's a very
has the state of the art in testing improved since then, though? I mean, I recall in the beginning, like when I started my career, like the idea of even doing any real unit testing was pretty novel. Now, maybe that's because I started from the wrong place, but
I still get, time to crash from new downloads to be, measured in minutes to days on things that I pull in fresh. So I think maybe it's improved, but I still see plenty of crash. Like things got more complicated too. Like, oh, everyone has to do GPU things, and they've got new libraries for doing Glide, OpenGL, blah, 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 whatever, followed shortly by somebody was busted on some funny hardware that they didn't foresee somewhere, and it crashed when I first downloaded and ran it.
Yeah, it's
I
true.
think one development that might help this approach is continuous integration, right? Because of course developers might not want to put this into their compile and debug cycles. That will be
Yeah.
practical. But I mean, it's not inconceivable that you could push your code and then it will be tested in this setup every once a day or once an hour or whatever.
You've had more than that. Yeah. I think the situation of testing has improved since I was doing stuff. I mean, Hotspot one of the first, or as far as I know, one of the first sort of large scale continuous integration and heavyweight testing frameworks. That was 25 years ago to get Hotspot to be stable. Yeah, there were a lot of works on my desktop, Aaron. That was the
Yeah, I'm thinking about some of the big mono repo companies like Google and Twitter and Facebook that often have a build server that is constantly running the build in the background so that you're not doing it on your own machine.
Yeah. And
If you have
testing-
some pieces of your code base that are moving really fast and some pieces of your code base that are moving really slow, that thing that nobody's touched in a year and a half, maybe it was worth spending 5 hours to compile it well because you only do it every year and a half.
So
The things that you're churning on,
Right.
you may not.
Although on the
first
other
time
hand,
you
if
turn
anyone
that-
goes in with any modification or improvement, then you end up with a gigantic performance regression to go with it.
when you first do the fancy thing on, you put at risk everything. So you have to sort of retest every baseline thing because the new code might be fucked up in some ways. Then you're all happy and it works. And then as Derek says, somebody changes something slightly simple and no one knows what. And the fancy optimality ain't fancy optimal no more, or it doesn't have the same performance. And you're very performance sensitive there. And
So you regress for 3 months while you're waiting for the super slow compile to get around to that.
well,
piece again.
or you diagnosing why it failed to do the right thing anymore. Like, Roberto says, hey, we had to go add rematerialization. We had to go add coalescing. We had to go add yada, yada, right? And then I'm going to use a new opcode that was available all along, but it just hadn't used it yet. So I SIMDized the code. And then the model, the optimal model doesn't understand SIMDizing. So suddenly he takes a 4x regression, right? And then I'm not saying don't do it. I'm just saying the flip of I'm going to use the fancy shit in production mode. It sounds really cool, but it is a thing that you take carefully. It can be done.
It costs you a cost model.
Yeah, right. You have to decide. Yeah, there's a business cost model, if you will, to flipping your compilation technology.
At the same time,
being
I
Mr.
think
Negative here.
some fancy things are already being shipped, like PGO. To my understanding, both Chrome and Firefox currently ship the official binaries with PGO enabled, and that enabled browser responsiveness to get something like 10% better, even though initial compile cost for Firefox nearly doubled. So it was still didn't worth it.
So it was worth it.
Yes, it was. I mean, browser responsiveness 10% better is still something that users may notice.
Yes, Cameron, I can see the lines. I didn't know that you could do that.
That would mean the center line of the distribution.
Yeah, just sound like yes. Did you hack the slides? You got a copy of the slides and hacked them and swapped them in? There's some technology here. Oh, so when he changes the slides,
I think he's just using the whiteboard feature.
yeah,
and
right.
his lines are
When
not
he
based on the
changes the
data.
slides underneath,
They're
we're going
based
to
on
have
design.
lines on the screen.
Hmm.
Yeah, okay, fine.
You're picking exactly the right color. That's it. I'm impressed.
So
Okay, now
it's a little hard
stop,
for me to
stop.
tell because this is on a log scale, but it looks
Yes.
like it's growing roughly linearly in the
Right,
amount of
exactly.
time
It's not
it takes.
linear because of the log, right?
Log, yeah.
It's polynomial
Right.
though. It's polynomial, so that's very interesting.
I mean, I can see that it looks polynomial, but
But there is
I would kind of like to know what the polynomial is.
Yeah, there is a catch here. There is a catch here that I must mention. Here are shown the functions which are solved to optimality. Sometimes in this 15 minutes time frame, the solver will not finish, and those points are not depicted here.
So if you finish early, what do you get? A pretty good or a I don't have an answer for you.
If it very often, so the solver has this kind of progressive behavior. So often you will get the first solution relatively quickly. And remember, we gave the constraint to the solver, asking it to get a better solution than LLVM, right? but very often the solver will have a hard time to prove optimality. So as more time goes, it will give you more and more solutions. But very often it gets stuck trying to prove whether this is optimal or not.
Hey, Ramos, go ahead. And we don't, you don't have to raise your hand. You can just chime in.
Cool. Yeah, Roberto, thank you. This is super interesting. Some of it is above my head. I'm more of a hobbyist than a professional, but I want to say thank you. And also I wanted to ask you the solver problem. Is that something that is parallelizable, or is it hard to parallelize that because of a lot of shared state?
It is parallelizable, and many solvers work in parallel. Like in theory, it shouldn't be too hard to parallelize a search. In practice, it is actually hard because of load balancing. You don't know when you take a guess, you don't know how much work is left to be done exploring one part of a search tree. You don't know how much work is left to be done exploring the other part, right? So that's a thing that makes it actually hard in practice. But there are some approaches like solving a portfolio of different solvers in parallel. That's usually a more pragmatic approach that works pretty well. That's because different solvers are implemented in different ways. They do different reasoning. They do different search heuristics and things. So they often complement each other quite well. So you might just trigger in parallel 10 different solvers on the same problem. And this kind of solvers, they often have like a standardized kind of input format. So you can really do the same problem to the same.
Can we use a function because it's a natural boundary in the code? It's relatively self-contained to use for the parallelization in parallel.
Well, that's the standard parallel make. C2 certainly does that. Parallel JIT compiles.
For the solver, I mean.
Yeah, right.
I mean, the solver, the unit of compilation for the solver is functions already, right? So, and of course you can parallelize above that, but that's outside of this framework.
I've certainly parallelized a SMT style solver before within a single solver. So I know it's doable. It's not actually that bad, or this particular one wasn't that bad.
So you're basically searching
most computers today have like these massive GPUs, right? Like, I don't know how crazy my GPU. It's got 32 gigabytes. It's, I never hit the boundaries on that one, but in my daily work, I basically never make use of my GPU. So it feels like, something is sitting around, just like, delicious coffee not being drank,
The GPUs are sort of poor quality for doing optimizing of code. That they're meant for doing graphics and triangle drawings and things. It's different problem solving.
So basically you're trying to search a large space, and the heuristics are what order you should search it in. So has anyone tried to use like AlphaGo technology where they're searching the giant space of Go or the giant space of protein folding for the space of doing these allocations?
I mean, there are lots of approaches that try to hybridize, pure constraint solving with all kind of meta heuristic for searching and so on. Yes. So that is an interesting thing. You model your problem, you model it carefully, and then there is a lot of development, lots of people out there researching on how to solve it faster and faster. So you can capitalize a little bit on that. My hope is that, by just me sitting here and doing nothing in 30 years, all of a sudden this will be realizable. Who knows?
So my question is, here the solver produces directly MIPS instructions and ARM instructions. Is that right?
Yeah, what it produces is a recipe to generate the assembly code. So it tells you
directly the assembly instructions for a particular CPU.
Yes.
Would it benefit to solve it for something like a bytecode, which is somewhere in between all of these?
You have to translate to machine code at some point, and the translation had better not lose the quality that you're getting out of your SMT solver. The translation has to be pretty transparent, and if it's that transparent, you just make the instructions.
It starts to look like x86 in some ways. They mimic it. So
what do you mean by it looks like an x86?
All of the instructions look like an x86 with few variants. Take for ARM, for example, it has almost identical equivalent instructions, if you will.
The other way around, x86 looks like every RISC chip on the planet.
Okay.
I don't know, maybe, yeah, but it's the RISC subset is the obvious thing you code for, and then
It depends if you think of micro-ops or the instructions. Arguably, in the instructions, the syst1, remember that ARM has added specialized copy instructions, which is exactly like a rep movements in x86.
I won't go so far as a micro architectural state. I will only reserve to the instruction levels.
So yeah, there is a big part in the model that is outside of that, and that is the cost model, right? And that can change a lot between different architectures. So what is the latency of this, or how many functional units of this type do you have, and things like that. And this is taken into consideration here.
Speaking of the cost model, how much can you tune the scheduling heuristics? I'm thinking of similar things to what LLVM's machine scheduler does. Heuristics like cluster, which clusters loads or stores together, so resource reduce, which tries to reduce the resources that are critical for a given instruction set. Is it possible to incorporate something like that to the constraint problem?
Yeah, as soon as long as you can express it in this mathematical way, everything is possible. Now, we didn't get very fancy with the cost model, to be honest. Our cost model really gives you can define a bunch of resources with a certain capacity, and then your instructions can use a subset of all those resources for different duration. That's kind of the
I was actually thinking about that, how easy it is to encode this mathematically, because for example, for this critical resource reduction, it is kind of self-dependent problem, because what becomes a critical resource depends on what instructions you are going to schedule. So I'm wondering if this kind of self-referential structure would be a problem or not, if you try to encode it as a constraint problem.
I don't think so. You could define variables that track this, and then so you can always define auxiliary variables that kind of track the state or your estimation of what the state is in the processor, and then constraints that.
I mean, is this heading down the path of doing the out of order modeling?
Yeah, this is something I have considered. We didn't do it, but I have a rough idea about how I would go about it. Yeah.
Can you describe it? What's the main problem with out of order?
So the main problem here is that the model kind of assumes that the instructions are executed as they are issued, right? So when it comes to what resources are going to be used and so on, which is not true for out of order. So what you would like to do is to perhaps refine this model so that you maintain these two views. One for register allocation, where you have your instructions ordered sequentially, right? One after the other. That's the way in which you emit the assembly code. And another one which actually captures the reordering that will happen in hardware.
So you need a reorder buffer model.
Yeah, and it's going to be a model, and it can be quite sophisticated and complex, I would guess, yes.
The reorder buffer model can rename registers as well, because the hardware is going to do that. So your rules on when a register can get reused might change.
Out of order, at least to me, out of order execution is more of an execution strategy of your already compiled code. It's just the processor decided to execute it in parallel but it keeps its promise along its architecture. Why is that? Why this may cause a problem for the
because the time at which a divide burns time on a divider unit, the registers got renamed, and so they are available. Whereas if a naive model would say the register has to be drugged forward with the divide op. Right?
Okay, for sure, it will mess the execution of the instruction.
Right, you need to break apart the architected register from the virtual register, the hardware virtualized register at the time the execution actually happens.
So basically, you will have to model what happens at both sides of the software hardware boundaries, right?
I was going to say, if you have a model of what the x86 is doing to compile to microcode, and you wrote your objective on the microcode that you knew would be produced from the x86 code rather than the x86 code
Okay,
itself.
Aaron, you got to show off.
That would be nice.
Come on, Aaron. Da-da-da! Woo!
That's our youngest coffee compiler club
Yeah,
member.
youngest member. There you go.
Nice colors on the screen, maybe.
Mm.
All right.
So Roberto, do you have more slides, or this is the
I do.
conclusion?
Just let me
Okay.
tell me to shut up when you get enough. You know.
Okay.
Otherwise, I will
Yeah, I'm ready for you to
or-
roll forward. But then we have to remove the extra bits on the slide share, and I'm not sure how to do that.
Oh, let me see if I can. I mean, if I move on, will I remove this beautiful art? That would be
Go do it. Go find out.
Oh, okay.
Cameron, I have to mark
You
it.
have to remove it now.
Yeah, the author can just go on top right. There's a little wastebasket you can tap to clear it out. There you go.
All right, who did the
Yeah.
little zigzag squibble, the check mark? That was somebody else exploring.
Yeah. Thanks.
Yeah.
Okay, so we looked and discussed a little bit about scalability, but what about code quality?
Yeah.
Optimal.
Optimal.
It's optimal, yeah, but what does it mean? So here
Okay.
here what I show is estimated speed up or LLVM, right? So I say estimated. So it's estimated according to the constraint model. It's a static estimation. And what we see is that for ARM, the speed up is not that large, right? Just around 1%, a few functions that reach almost 10%. But so here we have 100 functions, the 100 functions I mentioned before, and then the speed up over LLVM as a baseline. Speed up, not that amazing. And we see in general, in the cases where we get speed up, we tend to get better spilling and coalescing choices, basically. That's what buys us this small speed up.
I can't
Okay,
see on my
optimal, yeah.
phone. What's the highest speed up? Like the one around 77 or so?
Yeah, what is it? Between 10 and 15%, something like that.
Okay.
Yeah, the scale is like this because I show different plots on the same scale, right? Just to compare. So for MIPS, the picture gets a little bit better. And I mean, what does this tell us? This tells us that Unison is generating good code, but it might also be telling something about the quality of the LLVM backend and how much effort is it put there, right? So I don't know how much effort, for example, it is put into optimizing MIPS 32 code.
You could have
I mean, they've
sorted.
definitely put more effort into x86 than ARM than MIPS.
Yeah.
You could also have sorted your slides so the bigger speedups are on the right. You get a gradual curve.
Yes, I could do that.
Because it's
Again,
the
I wanted
same
to,
function, it's
yeah, okay.
more speed up every time or something.
That's true. I just took this straight from the paper, and they were all the same, so that you could compare. But you're right. In this setup, that would make more sense. Anyway, again, better spill code placement. That turned to be quite important, more than register assignment. So typically, many people focus about this coloring thing and optimal register assignment. And in practice, in my opinion, the way you do spilling is
yeah. I'll tell you. And of course, what C2 does is inline until spilling starts to hurt. And this is all about the spill code. And you always get a decent enough register assignment. Spilling.
Right.
So what do you think? What is the insight? What has led to the better spill code placement? Is it exactly the combination of register allocation and instruction scheduling?
Yeah, in many cases it is. And we actually run experiments where we only solve register allocation optimally, or we only solve instruction scheduling optimally, but separately. Right. So we did basically optimal register allocation and then optimal scheduling, or the opposite, sorry, optimal instruction scheduling and then optimal register allocation, right. And we got almost no speed up. Right. So it's really the combination of this. This is where the gain comes from.
Are there any heuristics that could be possible to extract from this and put in LLVM without the entire constraint solver?
Yeah, this is an interesting application, I think, of this technique. We explored a little bit this application in this collaboration with Ericsson. So they looked at the code that we were generating with this approach, and they were like, interesting. Yeah, maybe we could do this trick as well. And they learned a couple of tricks for their conventional backend.
C2 certainly moves instructions sort of locally, minorly, in an effort to save a register here and there, to save a spill here and there. There's no global brains, but there's definitely a local. If I just delay this a little bit, I can save a register, save a spill. That's what it means, save a spill. So I'm
Right.
willing
with
to.
measurable impact?
Yeah, at the time, yeah. I don't have a number off the top of my head, but I remember it was an interesting amount. There were certain functions that were hot in certain methods for which it was a much bigger gain, which is the driving, you know, you make the benchmark run faster, Cliff, okay. But it seemed to be, you know, interestingly non-zero in enough cases. To go on to the next one though, this is like, we got a lot of gains here.
Yeah, so here it's hexagon. Remember, this is a very long instruction board processor, so you don't only order the instructions, you actually decide what is scheduled in parallel with what. And this is a kind of processor, a kind of scheduling problem where you have the strongest interaction between register allocation and instruction scheduling. So if you do your register allocation bad, you can inhibit a lot of parallelization of instructions, basically, right? So you need to be careful when you do register allocation and so on. So this is the processor where it would make most sense to combine these two phases.
I would love to see the machine code before and after on that one guy who's basically double speed.
Yeah, I have a little demo. I don't know whether there will be time for that, but if not, the link is out there. You can watch it on YouTube. It's just 10 minutes, and it's not just a command line demo. There are some graphics.
I
Show
mean,
us.
we usually run, like I said, about 2 hours. We're at an hour and 15. I don't think anyone's in a hurry to leave.
Okay, I'm almost done with the presentation. If there is time afterwards, we can go quickly through it if you're interested. Right. So yeah, basically here we see better exploitation of this multiple issue capabilities of very long instruction words, so more instructions per cycle, simply. And also better speed code placement, so the combination of these two. But okay, here I showed you estimated speed up, right? But what does that mean? I mean, we could cheat and just, you know, say that we are best according to our cost model. Right? This is according to the cost model that we were using. So we actually wanted to measure.
The numbers on the previous slide weren't empirically measured times.
No, this is just a static estimation.
Yeah. Thank you.
According to the model that we are using. So yeah, it might be biased to our advantage, right? So we want to actually execute the code we generate. And for this, we focused on hexagon as the processor we've got the best speed up, just to see what was happening there. And for benchmarks, we picked MediaBench applications. MediaBench is this benchmark suite that has like signal processing and coding, decoding, and things like that you typically do in DSPs. And like I mentioned before, we didn't compile all the code with our approach, only the top or the hottest five functions in each benchmark. Right? It will take too much time, and we kind of pointless to compile everything with this. And to execute it, we use Hexagon Simulator. We didn't have access to the real hardware.
So it's estimated again.
Well, yeah, but in the manual, at least they claim it's 2% at worst, 2% off from the actual or something. I don't know.
It's not simulator. It's probably pretty good.
It's not cycle accurate, right? But it's said to be accurate. I cannot really answer to how accurate, but yeah, that's what we got.
It probably is pretty accurate, yeah.
And this is the figures that we got. You know, still a decent speed up here and there.
What's the plus and minus variation?
Yeah, so most of these applications are, you know, coders, decoders. So the plus minus, they indicate, you know, the sign or the direction that you go in.
So it's actually two different functions.
Yeah, two different applications.
Yeah, okay.
These are not functions. These are whole programs. Right?
Whole programs, right?
Where we pick the 5 hottest functions. So we are not compiling everything with our approach, only the 5 hottest functions.
Those are decent speed ups.
Yeah. And yeah, in average, something almost 6%. And there is a little thing here in this plot, something that sticks out a little bit. Do you have any?
You mean the minus?
Any remark? Yeah, you see this negative speed up here, right?
Yeah.
You might wonder, what the heck? We are generating optimal code. How can it be? How can it be worse than that of LLVM? And so this makes us wonder, you know, what is the accuracy of our cost model and our estimations, right? That is the next natural question to answer.
Well, or the Qualcomm simulator could be inaccurate as well, so it's fine. Yeah.
Yes, here we are assuming that they are not, but yeah, that is a risk in this experiment. Right. Anyway, so assuming the simulator is totally accurate, we run an experiment to see how far we were off from the actual speedup. So here we have estimated function speedup for each function and then actual function speedup, right? And if we have a perfect estimation, then we will see a line like this, right? And what we see in practice is this, right? So we have here one dot for each function, and then we measure the speed up, and then we estimate it, and then we see how far off they are from each other. So what do we see here? First of all, there's a strong monotonicity. This means that if our solver is telling us that we're generating better code, then it is likely that we are generating better code, at least. So that is something. But there's, of course, there are inaccuracies, right? So this means that if our solver is telling us we're generating code that is 10% better, it might be 10% or it might be 3%. It's not necessarily 10%. But at least from these measurements, we can infer that, we can infer that it kind of pays off in this approach to wait more time for better solutions, because there is this monotonic kind of statistical property that if a solver tells us that it found yet a better solution, it's going to be better. How much better, we don't know, right? And the inaccuracies came mostly from, so there could be two sources of inaccuracy here. One is estimated execution frequencies of the basic blocks in the compiler, right? And another one will be the dynamic processor behavior. And we did another experiment, and we found out that mostly the inaccuracy comes from not modeling things like branch prediction, cache misses, and things like that, which our model doesn't capture. But takeaway here is that more compilation time indeed gets you better code in this approach, and that's something. Any question about this, or should I move on?
I think we can move on here.
Right. Okay. Yeah. So finally, we wanted to try out. Remember, I mentioned we can optimize for different things by just changing the objective function. So here we took the same model and we just changed the objective function and say, now go optimize for code size instead of speed. And what we see is that by just turning this function, we actually get some code size reduction over the code generated by LLVM, depending on the processor, from 1 to 4% on average. It's very interesting because the solver changes the reasoning totally by just changing the objective function. Then the solver will generate totally different code. It will start caring, for example, a lot about coalescing, which it didn't care as much before, and it will not care too much about scaling. And sometimes you might see very interesting choices made by the solver. For example, scaling being subordinated to coalescing. So if it can spill in order to remove more register to register copies here and there, and if the numbers add up and this gives you a code size reduction, it will do it happily. It will spill as much as necessary if that gives you any gain in terms of code size, because you can do even more coalescing or something like that. So that's something that you will never expect from like, I think, a conventional compiler, right? The code generation strategy changes radically without you having to do anything. It also all of a sudden starts exploiting some processor-specific features, which it didn't care too much for speed. So for example, in the case of ARM, this small ARM processor, there is this thumb-2 mode, right? And then it paid a lot of attention into trying to encode instructions in 16 bits whenever possible, right? Even if that meant whatever, increasing the execution time of the program or whatever. Now we are optimizing for code size. That's all the solver cares about, right? So you need to be careful about what you wish for when you define your objective function. So takeaway in this case is that the approach really adapts to changing processor features, and processor features change a lot. New revisions of processors come and go all the time, and even changing optimization criteria, right? And that's what I meant when I said before that it's more flexible.
Yeah.
And yeah, it's time to wrap up the presentation. Like I said, this is a combinatorial approach, integrates register allocation, instruction scheduling. We have in our plan in our roadmap to also integrate instruction selection into the picture, but we never got there. So we ran out of funding, as it usually happens. It is practical for being a combinatorial approach. It models register allocation entirely, fairly scalable for being a combinatorial approach, and we can actually generate executable code and run this kind of experiments to see what is the actual speed up of the code we generate, which is an achievement in this context. And we see that it generates better code indeed than conventional backends. And the key for this is the use of constraint programming. Like I said, there are many other techniques like integer programming, SAT solving, SMT, and whatnot. But in this case, we found that constraint programming was the way to go to model this particular problem, because we can exploit all this dedicated reasoning that constraint solvers have for the kind of structures that arise in these problems. And we think this can be useful. We have touched upon this a lot. Of course, for compiler users, if you want better code, but also for compiler writers, because like I mentioned before, you can get inspiration by looking at the kind of code that it generates in certain contexts and maybe learn something for your heuristics in your conventional compiler. There's lots of work that could be done here, improving the cost model, integrating instruction selection, making it more scalable, of course. There are more tricks that can be used and so on. It's a never-ending list. And yeah, I think the link is to the project site where all the publications are and everything is available. What did you say, Cliff, in the Discord or something? So yeah, that concludes my presentation.
Okay. I'll
How
run for
complicated was building a model of the architecture? Someone wanted to like add RISC-V.
How
Would that
complicated
be-
it was. So what we did is that we extracted. So we based ourselves on LLVM, right? So we start from basically instruction selected low-level LLVM machine IR. They call it MIR, machine IR. And we use the same. We start from the architecture description as well, from TableGen. So we wrote a little tool that extracts all this and information from TableGen and generates that for this tool, which is kind of decoupled from LLVM otherwise. So once you have that, you get for free, all the definitions of what registers are used by what operands, by what instructions, functional units. All this you can get from LLVM. Then there is some effort that you need to put to glue everything together, for sure. If I wanted to model, I don't know, just to give you a feeling, if I wanted to model some RISC-V processor with the same level of accuracy as MIPS or ARM here, maybe that would take, I don't know, a couple of weeks, maybe week or something. Yeah, it's not automatic, but it's not terrible.
But it helps that LLVM can already target it.
Yes, I mean, yeah.
Thank you.
So please, before Alan, just a round of applause for Roberto's presentation and then go to questions.
Yeah,
Okay.
we can do that.
Okay.
And then I want to see demo.
Yeah. Do you want me to run, or should we do some questions first?
Well, I mean, I'll ask a question while you're setting up the demo, which will make you, distracted, of course. So the question I have, so about instruction selection, I know that, so Gabriel published like his thesis, and that obviously has, I mean, it lists all the constraints I need. So I'm just wondering, is there like, anything else that would help, or is it just the thesis? As far as as far as published material on instructions.
Anything that will help? What do you mean by help? Whom? Or
Well,
what context?
published material on it. I mean, there's a thesis, and I'm wondering if I'm missing any other good papers to read.
Well, I mean, he published a number of papers, but they must be listed in the thesis, surely somewhere in some section, the papers that are published. Then he actually wrote a book. So if you want to know everything about instruction selection, he wrote a book during his PhD thesis.
Oh yeah, that was like, I think I have the book. So, okay.
Cool. I will let him know. He will be happy to hear.
Yeah. Yeah.
I was sitting together with him in the same room, and yeah, I can tell you he put a lot of dedication there.
My question is how to debug the solver decisions.
Oh yeah, this is a whole area also in itself, how to debug it. One thing that has helped me a lot is visualization, actually. Look at the search tree that the solver is forming while looking for solutions, and then looking at individual points in the search tree. And yeah, try to visualize what's going on. It's a very different experience from debugging like imperative programs, right? Here, another thing that can help sometimes is if you are debugging. So sometimes, for example, in issues, you might get some over constraint model where there is no solution. You are trying to figure out why. You can just do bisection, like search, remove one constraint at a time, and then see. Yeah, I mean there is some research into how to make these solvers more debuggable, but I don't know. Those are the tricks that I used. I relied a lot on visualization. You will see some of it in the demo.
Cool.
Well, fire away the demo. I'm sure
Yeah,
more
okay.
questions will show up as we go.
Yeah, here it is. So it's on YouTube actually, so you can just watch it later if you want.
Well, we're hoping for you blow by blow as you go too.
Yeah. So I could play my own voice, but I think I could rather explain on top of it, right? That would be cheating. Yeah, let's move subtitles. So you see the video now, right?
Yeah, watching.
Yeah, okay.
Hasn't
changed.
changed.
No,
Yeah.
it hasn't changed, but soon it will. Yeah, so this is the function that I use for the demonstration, iterative factorial. That's kind of the hello world of compiler development, maybe, or at least for me, it's one of the first functions that I try out. It has 3 basic blocks, right? The initialization basic block, and then the main loop where we multiply and accumulate and decrease the counter, and then you return, basically. And so let's see how Unison generates code for this for hexagon. Right, so let me speed up a little bit here. How does the input format look like for us? This is what we get. It's nothing really extraordinary. It's just a control flow graph with sequences of instructions, which are already instructions selected. In this case, for hexagon, these are the pseudo names for hexagon instructions. SSA form, and then T7, for example, is temporary 7, and so on. So pseudo registers, right? This is the input format we get. It's basically LLVM MIR for people who's familiar with LLVM framework. Let's say about this. Let's see how it goes if we try to naive solve this. And by naive, what I mean is if we remove this propagation phase and we just try to explore by brute force all the possible combinations that we have to generate optimal code for factorial. Let's see how that will go. So here is the search tree, basically, as the solver tries to find, the best combination. And you see that the search space is huge. Now, right now, it's throwing like 50,000 nodes, something. And it hasn't found a single solution yet. So it hasn't found any valid assembly code yet. So I just had to stop it at some time, right? So you see that naively trying to brute force and trying to enumerate all possible combinations of decisions is totally unfeasible. Right? Just so that you get the feeling of how large the search space is. What happens if we add propagation on top of that? That is this specialized reasoning that removes invalid paths in this search tree. Basically, what happens is that we get the optimal solution right away. There is not even backtracking here, right? We just search, try one thing, try next thing, and we get the optimal solution already. As you might expect, because factorial is a small function, right? So here, I annotated each node with the decision that was tried out. First, we start by trying a certain global cost. So say, find me a function of cost 271. And then this means that we are trying to coalesce. Some O1 refers to operation 1, which is possibly a register-to-register copy operation. So we try to coalesce, and finally we do some small register assignment here. And that gets us already to the optimal code. Then the solver will backtrack and see that there is nothing else, nothing else, nothing else. And then it exhausts basically the search space and finds the optimal solution.
Why did you put a cost on there? What was the point of the 271?
Yeah, so basically there will be a cost variable telling you, all the possible costs, and the solver has different search strategies. But for illustration here, I just took a search strategy that takes the smallest, tries out basically the smallest possible cost, right? So the solver will enumerate basically all the possible costs for the code that is generated, and 271 was the smallest possible value there. So I say in the search, try the best possible one. Does it work? Yes or no? Next one, next one, next one. And here it finds already the optimal solution for the smallest possible code cost.
Right, yeah.
But those costs only have to be ordinal, not like linear or anything. As long as higher cost is worse and lower cost is better.
Right, exactly. This is a search strategy that works fine sometimes, because by selecting the smallest possible cost, you are constraining a lot the search space. Like, for example, many spill decisions will actually be removed directly because they are too expensive for that cost that you selected. And if you're lucky and then you find the solution there, it's already the optimal one, so you don't need to keep searching. So this is a search.
You're ignoring all branches that have any non-optimal cost just to prune the search tree.
Yeah. Yes. Find a coloring that involves no spilling.
Oh,
You had to spill, you lost already, so don't even bother.
And representing the cost function like a fitness function, does it mean it gets a better and better solution? It's monotonic, if you will, or from the worst solution that it finds to the best solution that it finds?
With this search strategy, it will not, right? Because the first solution you find is going to be the optimal one, basically. But there are different search strategies. This is something that I didn't touch upon, but the solver has like different phases in which it tries out different ways of searching the search space and things like that. This is just one of them, right? In which we kind of try luck, if you want. We go straight to try to find the optimal solution, and sometimes we try luck, and we get lucky, and this is convenient for this particular demo, right?
Yeah.
Go on.
Yeah, moving on.
Alan has a question, maybe.
well, yeah, I was just wondering what the cost function was, because you can't really predict the performance of a program unless you have the full program. So
yeah, so the cost function here, we are optimizing for speed again. So what I do is I weight each basic block by the estimated execution frequency, a static estimation given by LLVM. And then basically the cost of each basic block is the length of the schedule of that basic block, right? So that's it. It
reminds me of my compiler class where we were just like, assume every loop is taken 10 times.
Yeah, I mean, I reuse whatever logic LLVM has for estimating, but yeah, you cannot do much without profiling information, right? That's
I was taught 10 as well. So 40 years ago.
Really? I took that class in 2009.
Huh? Yeah, 89, 2009. There you go.
Right. So let's have a look at the data flow of this optimal solution that it found. This is the data flow within each basic block. So initialization basic block, this is the main loop, and then this is the return. And what we can see here is that, these are all the instructions that we got as input of the program. We have special instructions at the beginning and end of each basic block just to capture all the inputs and outputs of the basic block. And then we have one instruction that didn't belong to the input. It's this transfer. It's basically a register to register move in hexagon. So that's interesting that in the optimal solution, the solver decided to place this register to register move there right upon return. And we'll see why. Right, exactly, just showing you this. This is a visualization of the rectangle packing problem that I mentioned before for hexagon. I actually cut the number of registers for the sake of the demo. It has 32 general purpose registers, but this was too wide, right? An interesting aspect that I didn't touch upon is that we model, just like in C2 register allocation, we model here memory as if it were just more abstract kind of registers, right? So whenever you spill, all you do is that you assign these rectangles to the memory registers.
Register spills or stack
yeah.
slot spills or something. Yeah. Stack
Yeah,
registers.
exactly. That gives a very uniform, simple model, right? Yeah, interesting to note here is this move from T25 to T27. This is where the register to register move happens, right? And we'll see in a second why. And yeah, like I mentioned before, Hexagon is a very long instruction word processor. So this is a view of the scheduling part, right? We see, for example, that in the initialization block, 3 instructions are scheduled in parallel. And here, for example, there's one addition and one multiplication scheduled in parallel and so on. And this is what the solver is optimizing for, right? Make this as tight as possible in this case. Right. So let's compare the code generated for this factorial function for Hexagon between Unison and LLVM. Here's the comparison. To the left is the code generated by Unison. To the right is the code generated by LLVM. And I was actually quite surprised when I saw this the first time that, such a simple function as factorial, we get code that is slightly better than that of LLVM. The win is not huge, okay, because it's just that in the initialization block, we have one bundle, so all the instructions we can run in parallel. And in the case of LLVM, they have 2 bundles, right? I know, can you read this kind of assembly? Very long instruction word.
Yeah, I can read it.
Yeah, basically, these brackets, they indicate that all the instructions inside are scheduled in parallel, right? So we have these bundles of instructions being scheduled in parallel. So in the initialization block, in the Unison case, we have just 1 bundle. In the initialization block, in the LLVM case, we have 2 bundles. And why is this? The reason is that, just moving, the reason has to do with register assignment. Basically, the calling convention in the case of Hexagon dictates that both the first input argument and the return value need to be assigned to the same register 0. So because we have n as an input and f as an output, and they interfere within the loop, and they need to be placed in register 0 on input and register 0 on output, that necessarily needs to be a copy, a register to register copy somewhere to solve this interference, right? So how does Unison solve this? Basically, it assigns n to R0 from the beginning, and it keeps n in R0 through the entire life range of n. And it assigns f to R1 from the definition, and just before returning, it moves it to R0, right? Just like we saw before. It places this register to register move here right before returning. What does LLVM? It does kind of the opposite. It moves R from R0 to R1 directly at the beginning. There is this strange move from R1 to R2. I don't understand. There is no benefit in doing that, but it does that as well. And then it keeps F in R0 all the way. And I mean, if you consider these 2 choices, they're kind of opposite, but if you consider them from the pure register allocation perspective, it's not clear which one is better, right? They seem to be quite kind of equivalent, if you want. But, right, exactly, the difference is that in Unison, we do a register to register move at the end, and in LLVM, we do it at the beginning. But when you take into account the scheduling problem at the same time, you realize that if we do this move at the end, we can pack it in parallel with the jump and return instruction. If we do the move at the beginning, we increase the critical path of the initialization block. And all of a sudden, we need 2 bundles to schedule that, right? Here is the register to register move that LLVM chose to do. Yep. The problem with the case of LLVM is it will make this choice in the register allocation phase, and then it will move on. And then when it hits instruction scheduling, it realizes, oh, damn, now my critical path is 2 in the initialization block, but it's too late, right? And in the case of Unison, it will do this combined reasoning. What can I do in register allocation that makes sense for instruction scheduling? So that's how we get a little bit better code for Unison in this case. And okay, factorial is a tiny function, right? So I can show you code generated for something a little bit more substantial. This is just one function from MediaVent. I don't even know what it does, some signal processing thing. This is the control flow graph that we get as input. You see, it's not a huge function, but it's not a trivial function either to generate code for. And here I'm going to illustrate this iterative behavior that Unison has, in which it finds better solutions as time goes on, right? It has this progressive behavior. So at the beginning, there's some kind of pre-solving phase to improve solving, and then it goes on and it starts generating solutions. So let me see, in this iteration, it finds already a solution with a certain cost. Then it finds the next iteration, another solution with better cost. And then it iterates for a few times and it doesn't find anything better. And I kill it after 10 iterations, basically. But I could leave it go on. And if I left it go on, it will eventually find the optimal solution, but this eventually might be, you know, whatever million of years, you don't know. So here I cut it after 10 iterations. So what do we see? What the solver is telling us is that it found a solution that improved the baseline by an estimated 10% or almost 11%. This is a static estimation according to the cost model of the solver, right? And it's also giving us another interesting piece of information. And it's this optimality gap that you see above. What that means is that the solver can prove, oh, sorry, I shouldn't. Can you see this optimality gap, 0.7%? Yes?
Yeah.
So what the solver is telling us here is, I don't know exactly what the optimal solution is, but it's never going to be farther away than 0.7% from optimal. So that's quite interesting information. We know that we stop the search here. We are, in the worst case, we are 1% away from optimal. We might already have found the optimal solution and we don't know about it, but we are not very far off in any case, right? And that's a fair, you know, stopping criterion. I mean, that would be good enough for many people.
Is that the stopping criterion you used for the examples we saw earlier?
No,
or did you try to run them to optimality?
They're just, yeah, try to run to optimality and stop them at 15 minutes. I had more experiments you can read about in the top plus paper where I experiment with different optimality gaps and so on.
I don't really understand how, as this was producing output, it was repeatedly saying that it found the optimal solution and then it found a better optimal solution. Like, I thought the definition of optimal solution was that there could only be one.
It didn't claim to find the optimal solution. It found progressively better solutions, right? So
yeah, I'm with Derek here.
It found a solution with cost, what is it, 277 million, blah, blah, blah.
They go right up.
Is this finding optimal solutions in subparts of the problem space? Is like, because if you look here, it says, you know, 2/3 of the lines say it found an optimal solution.
Ah, yeah, okay, yeah, this might be a little bit confusing. This is finding optimal solutions for individual basic blocks. So basically the solver is arranged as a decomposition. It solves some kind of global problem first, and then it solves sub-problems for each of the basic block independently, and then it recombines. It's just a strategy that you can read more about. So these are locally optimal solutions, yes, for individual basic blocks. But then when they are combined, the solver sees that this is not the globally optimal solution yet.
Okay, and does your scheduling do anything between basic blocks, or it's local to blocks?
Scheduling is local. The only thing we do between basic blocks is take into account long latencies across basic, but we cannot move instructions across basic blocks.
Okay. But the input that you're getting before you, like, when the input blocks that you're starting with, are they already optimized somewhat by LLVM? Like, so that everything should be in the best possible basic block already?
Good question. I don't remember whether there is any I imagine there is something like that, but I honestly don't remember. So we escaped from LLVM right before LLVM does register allocation.
He surely has done some smarts about instruction placement then.
I think it does something at least locally to minimize or to reduce register pressure. It has some kind of register pressure aware scheduling phase.
Well,
Yeah.
the global code motion has already happened, probably.
Yeah.
Yeah, most likely. Right. So okay, so we found the solution that we claim is around 10% better than LLVM's one, and we know it's not far away from the optimal, but it's not the optimal. We have to stop the search because it will take too long time. How does the code compare? And this is a more substantial kind of piece of code. To the left, we have the code from Unison. To the right, we have the code from LLVM. And it gets tricky. There is no time to go to the nitty-gritty here and see what's going on. But we can see that we have basic blocks. For example, this basic block where we have 6 bundles, and then LLVM has 7. We have other, and this basic block we have 3 bundles. LLVM has 4 bundles, and so on. So we in general, in this one, we have what 3 bundles less, I think, than LLVM. So we tend to be able to schedule things more tightly, basically.
And is there any delta between the actual instructions being used? Like when I'm kind of looking at this, and it seems as though every instruction I can see on the left, I can see the same instruction on the right. But is it sometimes that an instruction will be substituted, or it's really just ordering and allocation happening here?
We can incorporate into this. So we have in Unison this notion of alternative instructions. So we can kind of do a little bit of instruction selection. Basically, we can choose among different one-to-one mappings between instructions. Yes, we do this, for example, to select for ARM, to select thumb2 mode instructions or regular encodings or things like that. Yeah. So you might find those kind of tricks here and there.
I can look at LBB03 block, and on the left I have a move U high and an if comp GTU in one bundle, and on the right hand side I can see that they're split into 2 bundles. For whatever reason, you couldn't recycle the bundle together, and that forced him to add a bundle.
Right. Basically, so in very long instruction word code generation, there is a higher incentive to do this together, right? Because there is this strong interaction between these 2 phases. You can screw up things easily by not being aware during register allocation of what you are doing.
Well, let's finish up here.
Well, I have a question.
That's the demo. Yeah.
Okay, so I timed it, and it takes about like maybe 5 seconds to generate the first solution. So,
yes.
So if you're writing a JIT, obviously you care about, generating, quick and cheap solutions. So I was just wondering, if there was, is it a good idea to use a constraint solving algorithm for if you want a fast solution, or are you better off just writing a register allocator for that fast path?
Well, yeah, if you really want compilation speed, then I would say don't use this. Yeah.
I mean,
constraint solver is fundamentally searching the problem space, right?
Yeah.
I mean, you could implement on top of the constraint solver your own search strategy where you mimic a heuristic, and basically you do a greedy thing, like a normal compiler would do. You might still get some benefits, like for example, correctness. Like the constraint solver will check that your solution is correct according to the model. That's something, right? But it's going to be always slower than doing your own dedicated code generator.
If you took you said you took LLVM as a lower bound or whatever, and you took equivalently C2, you took some other compiler who did some of the classic heuristics and said, I got this far. And does that help your constraint solver to do better? Get handed a solution that's not optimal. Does that speed up getting to an optimal solution?
Oh yeah, it reduces the search space brutally.
Okay.
I wonder to what extent you could use a tool like this to design the heuristics in other compilers and figure out, oh, we're randomly picking functions from the entire LLVM regression test suite. Did we beat it? What are the places where we beat it by a lot? And can we cluster the places where we beat it by a lot and say, there's a heuristic that we've missed here. You should always try to push your moves as late as you can, or always try to push your moves as early as you can.
Yeah. Like I said, we did that a little bit in our collaboration with Ericsson. I also have a presentation that is up in YouTube in some LLVM workshop where I highlight a couple of cases where Unison does substantially better than LLVM. And I recommend some heuristic tweakings in LLVM. So yeah, you could definitely use this for inspiration.
Yeah. It seems
So
like a very good tool for finding places where a heuristic is possible that really would help.
What I got is that the LLVM takes the optimization cases by cases, but the optimizer in Unison takes up for a bigger view, if you will, by holding on the global constraints and trying to according to its search cost function, combine the solutions, but not taking case by case, which sometimes help the optimizer to find a better solution. That's what I got from the presentation.
I think that's a good summary. So are you happy, or do you want me to keep talking for 2 more hours?
No, I was gonna just come up and say, let's wrap up. So any more questions?
Let me, let's see. I was going to ask about Stoke. I don't know. That's like this stochastic super optimizer instruction generator thing. So I don't know. I mean, the interesting thing it does is it uses Markov chain sampling. So like it explores the whole search space in like a random manner, and then like it optimizes the solutions it finds to make them faster. And so that's how they get avoid like this exponential explosion of search space. And I don't know.
Yeah,
I mean, I guess the question is whether there's a way in the register allocation or the instruction scheduling problems to figure out that like, oh, if I tune this, it'll be this better. But like if there's this notion of like solutions that are close to each other that you can use.
Yeah, definitely. I mean, there's this whole framework that is basically local search, and that combines local search with constraint programming, where you try to jump from a good solution to a slightly better solution, but doing local transformations. Like you start from LLVM solution, they said you try, okay, what happens if I swap this? What happens if I spill here instead of there, and so on. And you explore this neighborhood in the hope that you find better solutions in that way. So yeah, that's a possible technique you could use on top of this. Large neighborhood search is also a popular technique in combination with constraint programming. You remove, basically you undo a whole part of your choices. Like for example, you undo all the choices related to a certain basic block, and then you try to search for something else just in that said basic block, for example. That's another way of exploring, the neighborhood of solutions.
Would you see a path to integrating something like this in a production compiler someday, or would you still see the role as mostly focused on inspiration and searching for good optimization examples?
I don't know. I mean, it will not happen tomorrow, I guess, but it would be nice, to see in the future that a compiler that is just a solver. Who knows? I mean, solver technology keeps, improving, not only because we have better hardware, but also there are algorithmic improvements. For example, if you look at SAT solving and SMT, the improvement the latest 15 years or so is quite brutal, right? But of course, I'm not naive. I know that, this will not happen tomorrow, at least not for general compilers. But yeah, maybe in some use cases, like embedded systems, the use is not that far away from being practical.
So the main step to adoption would be better solver technology. fundamentally.
Yeah, I think everything that helps scalability, basically.
Right.
All right. You got one more,
Okay.
Alan?
Oh, and I have one question for Cliff, which is so what's the longest function you encounter in like the JVM?
Oh, machine generated ones.
Yeah, but like how many instructions is it? Since like Unison can only handle 1,000 instructions.
Oh, no. C2 will sort of semi-routinely handle things with 100,000 instructions.
Okay. All right.
I know there's some weird cliffs if a Java function gets too big that it just like doesn't optimize anymore.
No, right. So there's a 65K limit on bytecodes per function. And C2 has some cutoffs where he doesn't like to deal with things that look like they're going to be too huge just to keep life sensible, because if it isn't squared blow up. But if he's got some hot method and he's got a bunch of inlines, he'll just keep going. And after the inlining's done, he can be 100,000 instructions. It happens. I think that's a little more unusual, but it's not like every big server has a couple of those compiles happen.
Isn't there an iCache problem somewhere before you hit 1 million instructions?
Well, I said 100,000, but you
Or
did run
100,000.
iCache problem, yeah. But it's the hot code. So you got a meandering kind of uniformly smushy profile, and you're hoping most of it fits in your iCache and the x86 prefetches, but he'll fit in your L2. But yes, and it's not like you're stuck. Like if I do a machine generator function that's doing I've built a model for like machine learning. I built a machine learning model. It's a giant ass thing. I turn it to instructions. It's a giant wad of instructions. I'm just going to walk through. There's no saving it for your iCache. It's just too big. Suck it up, Buttercup. That's how fast it's going to go, right? This is not about inlining because you didn't learn inline. You just got here's a giant pile of bytecodes. No inlining. You're stuck. So if the profile's hot, I'll inline anyhow, and then it'll get big. And then the question is, was it better over not inlining? Probably I'm already dead on iCache if it's that big. And the inlining probably helps because there's probably internal loops, and the internal loops will all fit happily in your iCache. But yeah, instead the usual things are if you have a bunch of mediocre stuff, calling a bunch of mediocre stuff, he does start cutting off those so that you don't get there's no point to it because of iCache blowout. You don't inline mediocre hot into mediocre hot because you get iCache blowout. There's not the gain. But if you have one giant hot method and he's got hot loops internally, he'll take the giant method and start inlining the hot loops, and yeah, you blow out. But it's better than not blowing out that way because the inlining didn't change the actual execution footprint. It just let you optimize across the call boundaries.
Yeah, it's interesting because I always understood previously that you talked about inlining up until you hit the iCache limit and then stopping. But I guess there's also a mode where you go into where you just give up on iCache.
Yeah, if I have one method and it has hot calls that are hot enough, I'll say I'm going to let you get bigger anyhow, because I'm assuming all the not hot parts in the middle will blow through, and then you'll camp out in a hot loop somewhere in the middle. Like here's a giant ass server loop, the hot server parts in the middle. I still have to compile this. So I end up with big function, but the hot loop maybe fits in iCache. Like the inlining, the unroller tries really hard not to blow out your iCache. That's an easy one to blow out iCache on.
That's the message, hot method too big to inline or something.
If there's flags that deal with the numbers, it's a heuristic. So
of course, yeah.
Right. Yeah. So he says I have a total size, I have a hotness of this function, and I do some math on the combination of total size and hotness, and if it's less than some threshold, I inline.
And in that case, the function is huge. You've gotten to this point where you're doing this. Is there going to just be no unrolling or that type of expansion at all? You're going to sort of just give up on all that kind of stuff?
No. So unrolling and inlining run on different heuristics. The unroll assumes that I'm spinning in place. So that body of code wants to fit in your iCache plus having other stuff around. So I actually cut it like half your iCache at most. So the the body of the loop will be allowed to grow up to something like 16K, and it usually actually only ever gets to like 1K or something. It hardly ever gets that big. You have to try hard to make it unroll, because if it's a big loop and you unroll it, it didn't get much faster because you didn't have a lot of extra gains for unrolling.
Right.
But there is a count there that says unroll up to here and stop. The inliner says a different thing. Inliner says the whole guy, and this guy is a fraction of the whole guy, and this guy is below or greater some threshold compared to what I get when I'm done. Okay, throw it together or don't. Because it's usually all shades of gray. Like if you're really super hot in one place, it'll win every time.
Yeah.
But it's mediocre blah versus mediocre blah. At some point, you have to start cutting off.
Yeah.
I guess the loop guy assumes locally here at this point, I will be hot. The trip count here is big. So it's only this chunk of code I have to count for my iCache.
Yeah, that makes sense. Yeah.
Okay. Does anyone want to hear the GC question story that I threw in chat, or should we just close and be done?
Sure, if it's not too long.
It's not terribly long. This is in reference to people who are asking, like, how do I do GC and safe points and what's it mean? So the little loop just says, I have an array, I'm doing an integer find the element in the array, give the index. And the obvious thing to do is in the middle of the array, you're going to bump the pointer to the array as a pointer that's moving along, counting through the array. And unless you're an x86, you must have a bumped pointer in there. If you're an x86, you can do base in a register plus index or offset in another register. If you're any other hardware than an x86, you can't do reg plus reg as an addressing mode. So you have to have a non-pointer base in a register in the body of the loop. And that's sort of the trick. So
Do you want to share the instructions while you're describing it?
Okay, yeah, let's see here. Let me do that. Come back here, Zoom, come back here, share. I'm trying to figure which screen to go share. I will share my Emacs, I think, here, which I rewrote the loop slightly. And let me go do my font. Okay, so here, this is visible now to folks?
Yeah.
Okay. Yeah, okay, so fine. And I rewrote the loop only slightly, but I didn't really change the problem. So right here, I am loading from some register that's in the middle of an array. And right here, I'm bumping myself along. So in the course of GC, if I stop in this loop, R1 doesn't point to a base of an object, it points in the middle of an object. And that's the trick. That's the issue that you have to teach the GC what to do about. So if you are doing a non-moving conservative collector, Bloem collector, there's no bug and you walk away. As long as the Bloem collector can claim R1 might point to an array, the array that originally was pointed at, he'll keep it alive and you're done. It's all fine. If you're looking at a collector that's just trying to find whether the array is alive or not, and this is the last use of this array, is it alive? He has to reverse a pointer to the middle of an object to the base of the object. For some GCs, that's difficult. For some, it's impossible. I don't know of anyone who does it cheaply or easily. So when we were doing this in the land of hotspot, some of the GCs could reverse that and they didn't care, but it was expensive. It was relatively rare. It was okay. You had to take a safe point stop in the middle of the loop. For some other GCs, it was a hard stop. They couldn't reliably reverse R1 to the base. So the safe point notion here is if I stop at any point, I have to record everything, including the base for what R1 used to point to. And that gets big fast. So that was Alan's question about how big is your GC info. It's not just this register is or is not a pointer. It could be this register is a derived pointer. It's called derived in hotspot lingo. And here's the base. So hotspot would actually generate another register to hold the base. And then when he does put a safe point in, so if I put a safe point in this loop and I would put one in with, I'll cover in a second. If I put a safe point in this loop, it'll say this register is derived from that base. And then the GC can just do the delta math and move the base and then reapply the delta, and it's all fine. But the OOP map has to record not just a register that's a GC base, but also a register that's a derived and what it got derived from. So the next thing is, of course, the safe points often are the major cost in tiny loops because they require you to match the Java architected virtual machine state at every iteration, but the iteration only has, 5 or 6 instructions, most of which parallel issue anyhow. So any safe point will like double the cost of this loop. So for long running loops, I'll do unroll and jam. And that means that I'll unroll the inner loop a bunch and then no safe point in that. And then that has a trip count on it. And then I'll jam that in an outer loop, which is unrolled again, not unrolled. It counts again. Unroll counts at the inner loops. So every X iterations at inner loop, I'll take a trip in the outer loop, which will have a safe point. And that will divide the safe point cost by a sufficiently large number that I don't care anymore. And the usual cost I go for is 0.1%. About 1 in 1,000 instructions should have a safe point to deal with. And the safe point will cause you to have, 5 or 6 extra ops. And then the cost has disappeared. So the bug here is there is no safe point listed in the loop. You have a derived pointer in the body of the loop. How do you know if it's alive? How do you recompute the correct value if you move it? And that was for helping people understand what a JIT does with safe points here, or GC. So hotspot inserts another register with another value for the base to keep it alive. And then it has an OOP map that says, this is where it is.
I think your GC is too low level. Like, I'm doing garbage collection after I generate a control flow graph. So like, that's way before register allocation and any of that stuff.
Hang on. This has nothing to do with register allocation per se. At the time I hit the instruction I've got the cursor on, right here, there is no pointer in the system that points to the array base. There's a pointer in the middle of the array. There's nothing.
Find a pointer. I have a temporary, and it's not like the temporary goes away. I just use the temporary. And then it says, I'll keep a register around for the garbage collector.
You kept a register around for the garbage collector. I'm keeping a register around for the garbage collector. It's the same level in that sense.
Right, but like, it just happens automatically because I start garbage collection like way before I do any of the actual.
Okay, I'm confused about when you start garbage collection. Here I have this loop. It looks for an array. The loop runs for 1,000,000 years because I've made the array infinitely long. In the middle of the 1,000,000 years, another thread demands a GC cycle. You're in this loop. You break in the loop. Find the base for R1. Your GC cycle starts while I'm in the middle of this loop.
Well, I have a register, so
I'm saying you need the base. That's the trick.
Yeah, and so like I'm using signal handlers, obviously. So
you take a time interrupt. The timer says it's time to walk the GC forward. You take a time interrupt in the loop. So the signal interrupt happens in the middle of this loop. What do you do?
Right, and so then the signal handler gets the values of all the registers stored in the stack. And so
but the the original array without a temp, without another copy of it, the original array is in no register.
Well,
does that mean every single loop needs to have a save point to not kill GC?
It's in the register.
Okay, let's let Alan finish, and I'll go to Aaron. Say again, Alan.
So I said the array is in memory, of course, but the address of the array is in the register.
There is no pointer in any register to the base of the array.
Well, no, I added one.
Okay, so yeah, right. So you have to add one. So the JIT has to be aware that he has to have a base register hanging around.
Right. And so like, that's why I do garbage collection before I do code generation.
I don't understand what you mean by you do garbage collection before you do code generation. The code has been generated, then you ran out. Now it's time to do a GC cycle. What do you mean by doing garbage collection?
Like when I generate, okay, so I'm going to have some metadata for like garbage collection. So I'm going to generate that metadata
With your, yes, with your JIT code.
Before I
Totally.
do code generation.
Okay. So when
And
you're generating,
metadata is going to live with the code and as constraints. Well, and I'm going to handle those constraints while I do the code generation.
okay, so you've listed a constraint that says the base of an array has to be kept around until the last derived use goes away.
Yes.
Okay, and that's what C2 has, that constraint, but he doesn't do it in the way you're talking about. It doesn't do constraint programming, obviously. He maintains that he has to have a derived pointer around, and I mean the base if he has a derived around. And that's just the allocator has to deal with that.
Right.
Okay, Aaron, what were you going to say?
I was going to say, does this imply that you need to have a save point in every loop? Because some loops are small and you're going to get save points much closer than 1,000 instructions-ish.
Right. So
I mean, I guess you could unroll it a bunch and then put a save point in the unrolled thing, but
that's exactly what I'm talking about with unroll and jam. The original C2 that people lived with for a decade didn't put save points in tiny loops under the assumption that the time to exit the loop was low enough that we wouldn't mind stalling GC that long. Over time, there were some particular use cases where this was a fail, where the array was tiny, but so the array was large, but the loop was tiny. And it took him, you have 1 million entries, you're going to search 1 million entries, however many clocks per search cycle, suddenly you're at 10 milliseconds or 100 milliseconds on top of whatever the GC cycle is for GC pause, because this one thread is going to take that long to get a save point. So then we went to unroll and jam, where you would unroll the tiny loop enough times to drive the cost down to 0 and have an outer loop that would run the whole of the million iterations when the inner guy ran however many, 16, 24. But you didn't want to unroll it 128 times or 1,000 times because that would blow out your iCache. But you unrolled it 4 times or 8 times. Then you looped, but you said, if it's unrolled by 8 and I want to go 1,000 ops, I need to do 256 or 64 iterations or whatever the iteration count was. That's unroll and jam.
How would you deal with a small iteration count where each iteration takes a long time? Is it just naturally there's going to be some save points appearing inside the loop once it gets that big anyway?
Well, you'll make sure one's in there. So the save points start from the bytecode parser, and he puts one on every back edge and every function call. Then the optimizer throws them out. So you'll have one somewhere in that loop, but the loop may have been rotated if it had like an irreducible, because you had try catch finally crap going on. You get irreducible loops. He rotates the loops. He inlined it. He picked one set was inner and one was outer. He flipped them around because of profiles. Blah blah blah. Fucking knows. There's a save point in the loop somewhere. It's not anywhere obvious. Now there may be more than one. He'll start removing the extras until he gets down to 1. And then he'll look and say, is this loop big or small? And if it's small, I'll start unrolling it. And if it's really small, I'll do the unroll and jam hack, which he'll first start with. How big is the loop after I get rid of the extras? Now, if it turns out in every path through the loop, there's a save point already because every function calls a save point, then he comes and says, this loop isn't super hot, or I would have inlined that function call because that function calls unavoidably in the middle of the inner loop. So the loop's not that hot and I don't care, and I have a save point and I'm done. Or I inlined every function call in the hot inner loop, ended up with at least one save point, but maybe some extras. I'll get rid of the extras. Now I have 1. Is the loop big or small? Start unrolling if it's too small. So I can't add a save point later, by the way, because I lost the mapping to the architected machine state. I have to start with a mapping and I maintain it through the optimizer. And then I throw the extra mappings away as I get closer to code gen time.
Yeah, I've encountered that problem.
Yeah.
All right.
Okay.
Okay, one more question for Roberto. So let's see. So we talked a bit about you said it would take like 1 to 2 weeks to add a new platform to the constraint solving problem. So I was just wondering, in terms of the structure of the current Unison, like there's a GitHub and it has all this code apparently with Haskell code and C++ code, like since since I'm writing one from scratch, like would you make any major changes to the structure of the code?
Oh yes, I will. So I was young and naive in my PhD, and I wanted to explore new things. I wrote lots of Unison in Haskell for the fun of it. If I were to do it again, I would write it in a more mainstream programming language like C++ or whatever, perhaps more tightly integrated with a mainstream compiler framework like LLVM or something, and that would make it much more friendly, easy to use and adopt.
Okay. And but in terms of the major components, I didn't look at the that closely, but is there a component you think is missing that you'd like to refactor a lot of the code into or something?
I don't think there's an essential component missing, but I would definitely rewrite most of the components, and yeah. I mean, the conceptual ideas, I think are still fine, and I would kind of go the same way. I would perhaps target a different set of solvers, or like I said, the solvers keep evolving over time, right? So the solvers that were good choices at the time might not be the ones that are good choices today.
Yeah, I'm planning to write my own solver. It's just external solvers are slow, so it's just people don't want to wait for a process to spot, run, then there's how to communicate results. It's just too much overhead. So of course that means I have to make a solver. Which is
some solvers you can use as libraries and so on, right?
All right. Why don't we wrap up here? We're well after our 2 hours and whatever.
All right. Okay. I'm not hearing any major, oh, I messed up terribly things. So okay.
Every first attempt at any new project, you always make up bad mistakes that you regret later. It's just normal.
Yeah. Okay.
You go back through I would have done this, I would have done that. Yeah. It's all hindsight. Fine.
But how much trouble can putting the hash in the header cause?
Yes, exactly. Not that I would ever shoot the originators of whatever, Java. Fine. All right. It was very fun having you, sir. Thank you very much.
Thanks for having me. It was fun.
Entertaining and enlightening. It's all good.
Thank you.
All right.
Yes, thank you very much.
Thanks.
Great.
Okay.
Bye.
Bye, guys.